Hi boys and girls, this is lecture 6.8. The topic, Inverse Trigonometric Functions, Differentiation, and this will be part 1 of our discussion. Speaking of inverse functions, I wonder if the trigonometric functions have inverses. Well, here is the answer to that question. This section begins with a rather surprising statement. None of the 6 trigonometric functions has an inverse function. What? This statement is true because all 6 trigonometric functions are periodic and therefore are not one-to-one. Thus, we must define the inverse trigonometric functions on restricted domains. Here's what we mean. Notice we have the graphs of the 6 trigonometric functions here. For each of these to have inverses, they would need to pass the horizontal line test. But you can see they clearly do not pass the horizontal line test. None of them, which means they're not one-to-one functions, therefore cannot have an inverse. However, if we took just a section of the graph, we might be able to create an inverse. For example, what if we just took this section of the sine graph from negative pi over 2 to pi over 2? Then in that section, you can see that the graph passes the horizontal line test. Or what if we took this section of the cosine graph from 0 to pi? You can see in that section, the graph does pass the horizontal line test. Or perhaps here for the tangent function, what if we took the section from negative pi over 2 to pi over 2? Again, we have a section that would pass the horizontal line test. Therefore, with restricted domains, we can define inverse trigonometric functions. Here are the graphs of the 6 inverse trigonometric functions. Let's make a point about notation. There are 2 notations for inverse trigonometric functions. The first is this: y equals arc sine x. ARC in front of each of the 6 trigonometric functions indicates the inverse function. The other utilizes the exponent -1. Y equals sine to the -1, x indicates inverse sine. Note this is not the same as 1 over sine x. The exponent -1 is not indicating the reciprocal, it's indicating the inverse function. Here is a graph of arc sine. Notice that the range is from negative pi over 2 to pi over 2, which was the region that we isolated on the sine graph in order to define the arc sine function. Here's a graph of arc cosine, the range from 0 to pi, and that was the section of the cosine graph that we isolated in order to define the arc trigonometric function. Here is arc tangent, the range negative pi over 2 to pi over 2. Again, that was the section on the tangent graph that we isolated in order to define the arc tan function. And these are the graphs of the other 3 inverse trigonometric functions. Evaluating inverse trigonometric functions. First, we're asked to find arc sine of -1/2, which is really this question: sine of what angle is equal to -1/2? When dealing with arc trigonometric functions, we need to remember that there are clearly defined ranges, so our answers can only come from the range of arc sine, which is negative pi over 2 to pi over 2. We'll just keep that in mind as we look for our solution. I know that 1/2 comes from the 30, 60, 90 triangle, and so I can see that the 30-degree angle produces a sine of 1/2. But where is sine negative? In the 3rd and 4th quadrants. However, remember that arc sine has a range from negative pi over 2 to pi over 2. Thus, my answer can only come from these 2 quadrants, and that narrows it down to the 4th quadrant. Therefore, the 30-degree reference angle in the 4th quadrant is my answer. That will be 2 pi minus pi over 6. Since we're moving backwards into the 4th quadrant from 2 pi to get our solution, and that's going to be 11 pi over 6. Now let's look for arc cosine of 0. Again, that's asking this question: cosine of what angle is equal to 0? And what is the range of arc cosine? From 0 to pi. So I'm not going to use a triangle here. I'm going to look at the cosine graph to determine where cosine is 0. From 0 to 2 pi, it's 0 in 2 places, at pi over 2 and at 3 pi over 2. But remember, arc cosine is defined only from 0 to pi. So out of those two options, I know that pi over 2 is my answer. Now let's look at arctan of the square root of 3. This is asking the question, tan of what angle is the square root of 3? And arctan has a range of negative pi over 2 to pi over 2. Again, square root of 3 comes from this reference triangle. The angle that has a tangent opposite over adjacent of the square root of 3 is the 60-degree angle, pi over 3. I know that tangent is positive in the first and the third quadrants, but again, since arctan has a range only from negative pi over 2 to pi over 2, I know that we're going to be referring to the angle in the first quadrant, which is pi over 3. Finally, we're asked to find arcsine of 3/10, which is this question. Sine of what angle is equal to 3/10? Well, this doesn't come from any reference triangle, so I'm just going to use the arcsine button on my calculator. Arcsine of 0.3 is 0.305. Make sure that your mode is in radians. Let's use right triangles to find trigonometric ratios. We're given that y equals arcsine of x, y is between 0 and pi over 2, and we're asked to find cosine of y. Y equals arcsine of x can be rewritten this way. Sine of y is equal to x. In this triangle, the angle y is labeled. Sine would be opposite over hypotenuse. If I make x x over 1, that means I can label the opposite side x, the hypotenuse 1. With these two values and the Pythagorean theorem, I can find the value of the adjacent side, which is going to be the square root of 1 minus x squared. Remember, we were asked to find cosine of y. So without actually having to find the value of y, I can say that the cosine of y is the square root of 1 minus x squared. In the next example, we're given that y is arcsecant of the square root of 5 over 2, and we're asked to find tangent of y. So let's rewrite this statement as secant of y is equal to the square root of 5 over 2. Well, remember that secant is hypotenuse over adjacent, so that means these sides can be labeled square root of 5 over 2. Using the Pythagorean theorem, we can solve for the other side. That means the square root of 5 quantity squared minus 2 squared will be our missing side. And that's going to be 5 minus 4, which is 1. So the side opposite the angle y is 1. Now we're going to be able to say that the tangent of y, which is opposite over adjacent, is 1/2. Now let's discuss the derivatives of inverse trigonometric functions. We have discovered that the derivative of the transcendental function f of x equals natural log of x is the algebraic function f prime of x equals 1 over x. You will now see that the derivatives of the inverse trigonometric functions are also algebraic, even though the inverse trigonometric functions are themselves transcendental. Let u be a differentiable function of x. Then the derivative of arcsine of u will be u prime, the derivative of u, over the square root of 1 minus u squared. You can see that the derivative of arc cosine is the negative of that same value. The derivative of arctangent of u will be u prime over 1 plus u squared, and the derivative of arc cotangent will be the negative of that value, and the derivative of arcsecant of u will be u prime over the absolute value of u times the quantity the square root of u squared minus 1, and the derivative of arc cosecant u is the negative of that same value. In our last example, we're going to differentiate inverse trigonometric functions. Once you've memorized the derivatives of the inverse trigonometric functions, the derivatives are pretty straightforward, but it is helpful to identify a few key things first before taking the derivative. Obviously, it's good to know what u is. U in this case is 2x, because you will need u prime, or du, for the numerator of your derivative, which in this case is 2. Another helpful thing to find is u squared, because the denominator of each derivative has a u squared term in it. So u squared would be the quantity 2x squared, which is 4x squared. Now you're ready to take the derivative, which will be u prime, which is 2, over the square root of 1 minus u squared, which is 4x squared. For the second example, u is 3x, du is 3, and u squared is the quantity 3x squared, which is 9x squared. Therefore, your derivative will be 3 over 1 plus u squared, which is 9x squared. For our next example, u is the square root of x, which can be written as x to the 1/2. Therefore, du is 1/2 x to the negative 1/2. And u squared will be the square root of x quantity squared, which is x. So our derivative is going to be du, which is 1/2 x to the negative 1/2, over the square root of 1 minus u squared, which is x in this case. Let's rewrite this. We're going to have 1 over 2 square root of x, square root of 1 minus x, and these two can be combined since they're both under a radical. 1 over 2 square root of x, 1 minus x. For our last example, u is e to the 2x, which means that du is 2e to the 2x, and u squared will be e to the 2x squared, which is e to the 4x. Therefore, your derivative will be du, which is 2e to the 2x, over the absolute value of u, which is e to the 2x, times the square root of u squared, e to the 4x, minus 1. Well, these two e to the 2x's cancel, giving you a simplified derivative of 2 over the square root of e to the 4x minus 1. That's it for today's lecture. Here we have the graphs of all 6 trigonometric functions combined. Just for fun, can you name one place where this is happening? God bless you, boys and girls.